first video in the series, we'll focus on the method of least squares, which is one of the most sort of intuitive and easy to explain ways of thinking about fitting a line to a given set of data. We're going to use a toy example before we get back to our real examples in the first introductory video. And that toy example is going to have the 5 data points shown in the table on the left and also plotted in the figure on the right. Now, notation throughout this video, we're going to use the notation xi, yi to refer to the ith data point in our sample. And we'll use n to be the sample size. So in this case, n would be 5, of course. Right. Now, we could draw a lot of different lines, right? There's no one line that will fit through all this data, but we could draw a lot of different lines that would kind of capture the overall trend. One might actually pass through the first point 0,1 and kind of split the difference between the other points like that. Or we might try and split the difference in some other way. And our goal is really to figure out, well, out of all these possible lines we could choose, so out of all lines b0 plus b1 x that we could choose, which b0 and b1 kind of give us the best overall fit to our data. So here's 2 examples, basically the 2 lines I sort of attempted to draw in the first video. The orange line is 1 plus x, and the blue line is 1.4 plus 0.8x. Okay. So to assess how well these lines fit the data, they both look decent, right? The orange line actually passes through 1 point exactly and kind of like gets roughly the same, roughly evenly close to the other points, whereas the blue line kind of splits the difference between them all, right? So for any particular point, to analyze how well the line does at predicting its value, we could look at the difference here between the actual and the predicted value. So for example, for the blue line, the actual value of y when x is 1 was 3, right? So there's the actual value, y equals 3. But we also get a predicted value, y hat, which it looks like here is about 2.2 or something like that, 2.3. Okay. So for that particular data point, the error made by the blue line was 0.8. Okay. Whereas the orange line makes a slightly bigger error. Okay. Right. If we wanted to go down to the orange line now, we'd need to add in this extra little bit. And so for that particular point, the blue line provides a better estimate. But for some of the other points, like this first one, the orange line provides a better estimate. So what we'd like to do is for each data point, we're going to compute the difference of y minus y hat. So we're going to compute all these yi's minus y hats. We're going to square them because we'd like to take into account the magnitude of those differences and not just whether they're positive or negative. And we'll add them up. And we're going to use this sum of squared errors as a measure of the goodness of fit for our lines. Okay, this is what we'll call the sum of squared residuals for our fit, right? The differences between the y's and their predicted values. So in the table on the right here, that work is done for us by R or Excel or whatever I decided to use for this. Okay. The first column here is the x values, then we have the y values. Next to that, we have the predicted y's based on the orange line equation, the predicted y's based on the blue line equation, and then the squared errors for each point and each equation. And these numbers at the bottom here, okay, these would be our sum of yi's minus yi hat squareds. So obviously, a smaller sum of squared residuals, or sometimes also people say sum of squared errors. I'll just point that out now. All right. This one has a smaller sum of squared errors, and hence we would say that this blue line provides an overall better fit to the data. Okay. But ultimately, of course, our goal is how do we find the best out of all possible lines, right? Because I just picked 2 of them there, not really totally at random, but somewhat at random, and we'll see what happens. So the least squares line is the idea that given a set of points xi, yi for I equal 1 to n, the least squares line, y hat equals b0 plus b1x, is the line that minimizes the sum of squared errors, L, which we're going to call L of b0 and b1. So think of this as a function of the intercept and the slope. Right? For each possible intercept and slope, it makes a prediction. So these are what we were calling our y hat here. and excuse the missing I next to the x there. Okay, so this would be y hat I, the prediction for the ith point. And we're trying to find the b naught and b1, which minimize this sum of squared errors over all possible choices of b naught and b1. So it's actually not too hard of a problem to solve. It basically boils down to Calc 3. We're going to take the partial derivatives of this function L with respect to b naught and b1, set them equal to 0, and see if we can solve the resulting equations. So starting with dl db naught, right? We differentiate inside the sum, and we use the chain rule. So that's going to be 2 y naught minus b naught minus b1 xi, and that xi is missing again. Apologies for that typo. And then times the derivative of the inside with respect to b naught, which is negative 1. Right? So now we can actually simplify this out by pulling the sum. So inside, so I'm going to pull out the 2, and then I'm going to get, and I'll also pull out the negative 1. Then we're going to get sum of yi's, okay, minus, now beta naught's a constant, so when I sum up from 1 to n, I'm just going to get n times beta naught, and then minus beta 1 times the sum of the xi's. And remember, we're trying to set that equal to 0. Okay. So if we rearrange this a little bit, right, we divide both sides by negative 2, we're going to end up getting n b naught plus sum of the xi times b1 equals sum of the yi. And I'm writing it in this way because remember, our unknowns here, in fact, let me highlight them in red. Our unknowns here are b naught and b1, whereas the coefficients, the n, the sum of the xi, and the sum of the yi, those are just going to be some constants that will be computed from the data, right? So that's one equation for the two unknowns, b1 and b naught. To get a second equation, we look at the other partial, dl db1. Right, so using the chain rule again, we get 2 yi minus b naught minus b1 xi. Now, though, when I differentiate with the inside with respect to b1, I'm going to get a negative xi here. So again, breaking up the sum, we have 2. But now I need to multiply, and I'll factor out the negative again as well. Now we need to multiply each of these terms by xi. So I end up with yi times xi. We end up with a minus beta naught times sum, oh, there's one of those random lines again, times sum of xi. And then finally, minus b1 times sum of the xi squared. And we're going to set that equal to 0 as well. And when we do so, we end up with an equation sum of xi times b naught plus sum of xi squared times b1 equals the sum of the xi times the yi's. And again, just to emphasize here that the b naught and the b1 are the unknowns. I'm going to highlight those in red. So this might look ugly, but remember, all of these coefficients here, highlight them blue, are just numbers based on the data. And this is just a simple equation, system of two equations, two linear equations in the two unknowns b naught and b1. To eliminate one of the variables in these two equations, we could, for example, multiply the first equation by the sum of the xi and multiply the second by n and then subtract. Doing so will result in an elimination of the b naught terms from both equations. And in the first equation, we'll get a sum of the xi squared times b1, and in the second equation, we'll get minus n times the sum of the xi squared times b1, right, after factoring out b1. Now on the right-hand side, we're going to get a sum of xi times sum of yi minus n times the sum of the xi yi's. And these are not the same thing, right? In the second sum here, the sum of the xi times yi's, I multiply the x's and the y's together first and then add them. In the first sum, I add all the x's, add all the y's, and then multiply them. And those will obviously give us two separate answers. So just if we divide both sides by the coefficient of b1, And I'm also going to factor out a -1 from the numerator and the denominator just to make these formulas look maybe a little more familiar for those who have seen them before. We would end up getting that b1 is the sum of the xi, yi, minus the sum of the xi times the sum of the yi. And then the denominator n times the sum of the xi squared minus sum of the xi all squared. There. Okay. So that's our formula for B1, and it's actually fairly simple to compute, right? We'll see how to do it with our data in a second. But I do want to go back and note that from the first equation here, this equation 1, if you solve that one for B naught, notice that what you end up getting is that B naught is 1 over n times the sum of the yi minus B1 times the sum of the xi. So, or actually even simpler, it's y bar minus B1 x bar, okay, if we multiply through by the 1 over n. So the format is first you compute all these different quantities involved in B1. So there's a sum here, a sum here, a sum here, and a sum here. So we need to compute those 4 things, right? Because this one also appears here. You compute B1 from that formula, and then you use your answer and plug it in here to compute B naught. To illustrate how easy those formulas are to work with, let's compute both coefficients B naught and B1 for our toy example of data. And all this code will be also posted in a supplementary file on Canvas for you to look at your leisure. In fact, I encourage you to pull it up now and follow along as I discuss. So the first 2 lines of this code here simply enter in the observations. So the x values range from 0 to 4 spaced by 1. This is kind of a shortcut for doing that in R. The second y values are 1, 3, 2, 5, and 4, which I'm just entering as a list. N is defined as the length of x, so it's the number of observations. I'm going to use the notation SXY to denote the sum of x times y. So notice here I'm multiplying x and y together first and then taking the sum of the resulting values. I'll use SY for the sum of the y, SX for the sum of the x, and SXX for the sum of the x squareds. So once I have these 4 quantities, actually these 5 if you include n, I simply compute B1 as n times SXY minus SY times SX. That was the numerator from our formula. And then n times SXX minus SX squared. That's the sum of the x squared. We then compute B naught as the sum of the y minus B1 times sum of x over n, and then look at the results. So once we do that, we see that we get 1.4 and 0.8. So whoa, now you see where that blue line came from on the first page. Not totally random after all, it was the least squares line. At this point, I know you're probably thinking, I don't give a shit about that toy example. I want to hear more about corona deaths and baseball. Well, the baseball problem is actually one I'm going to leave as a quiz question, where you'll be asked to investigate various properties of the least squares line for that example. However, I did want to make a few comments about the coronavirus one, because that was a situation where the response variable, which I'm going to call W for now, was not linearly but exponentially related to the explanatory variable date. Right? And it was only after taking a log transformation that we saw a linear relationship between x and the new response variable y, which was log deaths. So just to kind of decompose why that's happening, let's take a look at the situation where we're assuming our y hat is a e to the bx. So we have an exponential model for how our response is related to our predictors. Well, if we take log of both sides, then we get the equation log of w hat equals log of a plus bx using properties of logarithms. And if I relate this back to now y, which is log of w, we can see that this equation is simply y hat equals b naught plus b1x, where b naught is log a and b1 is the same as b, right, the same slope. So if I can fit a least squares line to the log data here, right, I can relate it back to my original data by just taking exponentials of both sides of the equation. After discussing that connection between exponential and linear growth, we can go back into R and actually compute coefficients for our COVID deaths model. Now, the first thing you're going to need to do if you want to reproduce this code is load the COVID deaths data into R, and that data is available on Canvas. Note that relative date means days after March 1st, which is when that sort of exponential growth started. So our independent or predictor variable in our model is going to be relative date. Our response variable here for the purposes of fitting the line is going to be log deaths. The next few lines of our code simply reproduce what we did for our toy example, computing all the sums, computing the coefficients b1 and b0 based on our least squares formulas. And we can see that when we do that, we get an intercept of 1.08 and a slope of 0.228. Now, in our real world application, remember all these are happening on a log scale. So this 0.228, this is basically, think of this as the coefficient in the exponent of our growth. Okay. So to see how well our model did, we're going to plot x versus e to the y. So this is now our actual number of deaths versus date. And we're also going to plot our predicted deaths on that actual level, which is just the exponential of our least squares line. And when we do that, we can see that our model does indeed provide a pretty good fit. If anything, in the last few days of March, it seems like maybe the number of deaths actually were slightly above this curve, which is a little troublesome. So to conclude this video, I wanted to show you an example of how you can use such models to extrapolate into the future. But I want to give a word of caution before you do that. Extrapolation based on such models is dangerous because things can change, right? At any point, the coronavirus could peak, at which point this exponential model would no longer be valid, and we would go shooting off in the wrong direction, and well, our points would start to level off. Okay. Second, we can do things to affect this trajectory, things like we're doing right now, right, with keeping a responsible radius, isolating ourselves at home, staying away from others. Those sorts of things can stop the spread and hence stop the total number of death rates. But I wanted to show you just kind of some estimates that we get from our model if for some reason the coronavirus continued to spread at the rate it did now and we did nothing to stop it and it didn't reach its peak before these times, what would happen by certain dates in the future. So the three dates I'm going to choose are April 15th, April 30th, and May 15th. So I'm going to enter those dates in terms of how far they are after March 1st, and then I'm just going to use our model, right, to compute the expected number of total deaths by those dates. I'm just rounding it off to the nearest integer, which is that round function. So you'll notice that if we did nothing and coronavirus continued to spread, by mid-April, we'd have about 86,000 deaths, which is bad, but it gets much, much worse. By the end of April, we'd have 2.6 million deaths, and by mid-May, we'd have over 82 million deaths. Okay. Now, of course, these are not going to happen. These no, better not happen. But again, I just wanted to kind of give you some of the reasoning that experts are putting into this and why exponential growth of disease really is so scary. So in the next video, we're going to take a step back and reapproach this problem of curve fitting from a maximum likelihood perspective, and that will allow us to not only obtain equations for the least squares line, but get confidence intervals for their estimates and whatnot, and do inferential statistics and other things like that.